EEG signal analysis for human cognitive assessment. So before we start, let us thank Samriddhi Mohdiwale for her work, and I am using her contents for this lecture. So let me thank Samriddhi before we proceed to this lecture. All right. So EEG signal analysis for human cognitive assessment. If I rephrase the title, EEG signal analysis for human cognitive workload assessment. When we are engaged in some activities, how much workload, especially cognitive workload, is there on our human brain? How can we assess? How do we assess that cognitive workload using EEG signal analysis? Let's talk about. So as I told you, this has a lot of practical work. Let's understand human cognitive assessment. What do we mean by human cognitive assessment? So assessment, the cognitive assessment is actually used to evaluate the brain based attention, how much load is there on the brain related to attention, reasoning, thinking, planning, categorizing, remembering, decision making, and so on in our daily life, in day to day life. So when we are paying attention, say the pilot who is working in aeroplane, so and some other people who are engaged in some activities where reasoning is involved, thinking activity is involved, we need to plan in some activities. So there it is actually causing some workload on our brain. So this is the topic all about cognitive assessment, cognitive workload assessment. How much workload is there on brain when we engage ourselves in either paying attention, reasoning, thinking, and so on. So these tasks which involve attention, reasoning, thinking, etc. are actually outcome of learning processes. If you are paying attention, if we are doing some reasoning related task, that always involves what we call as a learning process. To assess the cognitive workload, there are different measures which are used. Subjective, it is actually subjective. In fact, cognitive workload is a subjective matter. It can vary from one person to other person. Then it also is a type of behavioral, behavior also affects the cognitive workload, and of course physiological measures. So the physiological measures are one where the physiological parameters are used. EEG signal analysis is one of them that falls under physiological measures. Cognitive processes include, what do we mean by cognitive processes? Where we have some workload, motor imagery. So number one is motory task. Means something we are, controlling the different motory tasks with our brain. We are moving our eyes, hands, and other parts of the body, which is controlled by the brain. So motory task and motor imagery, then attention, working memory, the memory which we are using for a certain task currently, and the cognitive workload. These are the processes. And what do we understand by EEG signal analysis? We have actually explained this in very detail in our previous lectures. But since the cognitive workload assessment, the assessment which we are going to discuss in this lecture, is utilizing completely the EEG signal analysis. So let us revisit what do we mean by EEG signal analysis, and that too in context with the current work. So we all know that in EEG signal analysis, these are the major stages. The data acquisition and pre-processing, we have discussed in detail in previous lecture. Channel selection, I have already explained you, because from all the channels, huge amount of data comes and we need to optimize the channel selection, and similarly feature extraction and feature selection. We extract the features after pre-processing the data, and we also select suitable number of features. So in this particular slide, I have only highlighted these two topics or these two components, two stages in blue color, because this particular work has mainly, address channel selection and feature selection for better or for efficient cognitive workload assessment. Then comes, once you have decided the optimal number of channels, optimal number of features, then you go for classification, where we use suitable classifiers. And if you remember, or if you are good in artificial intelligence or any ML techniques, so you know it very well that classification and regression are the techniques where there is some difference. This is not clustering, of course. Classification, you classify the data in binary groups, whereas or discrete groups, whereas in regression, you get the classification in continuous groups. And then, of course, performance is evaluated. You need to understand whether the signal analysis, whether a particular classifier is performing well or not. If you have used a classifier, say SVM, support vector machine, or any other classifier, how it is working for your application, you can compare SVM with other methods if you have tested, or you can also compare with other existing methods. So this is a rough block diagram, but this block diagram is a practical block diagram. What we have used in our work, EEG signal was acquired, but we did not acquire. We used this particular work was on a standard data set. There is a standard data set, BNCI Horizon data set is there for EEG, and that data set was acquired and it was subjected for pre-processing. We have talked about what is the role of pre-processing. And then we extracted, in some tasks, we extracted wavelet features, and in some other application, we extracted other features. So I'm going to talk about all those tasks where we extracted the features, and after extracting the features, we optimized the suitable number of features, and those features were sent to the classifier, and then finally classifier resulted the cognitive workload assessment. How? Let us understand. So the research problem or the scope of work which is there is channel selection method is a very less explored for the cognitive state assessment or cognitive workload assessment. There are in fact very limited research in the area of cognitive workload. You will not find much amount of research in this area. And even if the research is there on cognitive workload, in in very few research work, channel selection method has been emphasized. So therefore, the channel selection method is one of the major objective. Channel selection is the major objective in this particular work. Extracting high dimensional features always results in curves of dimensionality. If you extract huge number of features, so dimensionality of data increases. And of course, when there is a dimensionality increased, then that increases the computational complexity. So how to deal with more number of features, how to deal with the reduced number of channels are the major research scope of this current work. So less features, of course, there is one more, interesting thing at the same time. We need to keep in our mind that when you go for reduced number of features and when you actually get less number of features, the performance may be compromised. So you have to always have trade-off between the performance of an overall system and the number of features. It means you cannot reduce the number of features to very minimum so that the performance of your that system is degraded. So therefore, optimal manner, you have to reduce the number of features as well as channels in the optimal manner so that performance is not compromised. So there is need to maintain trade-off between accuracy and the feature space. Feature space is nothing but the space of all the feature vectors. How do we create feature vector? I have explained in the previous lecture. Set of features we represent in the form of matrix or in the form of vector. It is useful. All these analyses are useful, particularly cognitive workload assessment is useful in the air traffic control. I was talking about how much stress, how much workload the pilot is undergoing in different situations and conditions, working under the control of air traffic control. The people who are working in ATC, air traffic control, medical science, those who are working in medical science for different purposes, medical rehabilitation, patient care, treatment, and all that. So you know that very well that especially, particularly if you see during COVID-19 pandemic, how the medical science people were in tremendous stress and tremendous workload. So how much the cognitive workload affects, and how it can be assessed so that we can understand whether it does affect the health of the person who are involved in such task or not. Similarly, in the road and transportation of driver safety, if the driver is busy driving the truck or the car for a long time, how much workload he is having, that all analysis comes under the scope of the present work. What I'm talking about, assessment of cognitive workload. Automated models can help to assist the psychologist, those who are working in the area of psychology, neuroscientists for early and accurate diagnosis of mental disorder also. If we can find out the cognitive workload and there is imbalance in the cognitive workload, there, psychologist and neuroscientist can come into picture and they can help the person and detect the difficulty at early stage so that the subjects can be motivated or guided or advised for the suitable diagnosis. So this particular flow diagram is an interesting diagram that gives the complete picture of the work which was implemented by the scholar, signal processing, signal acquisition, with which we sorry we begin our task, and then it goes to signal pre-processing. After pre-processing, it goes to different stages. We have divided the complete task in three to four phases, phase A, B, C, D. And finally, all these tasks are performed. Then it goes to classifier. And after classifier output, the classified output goes for we evaluate the performance. Then we do the comparative analysis. For example, if we use a number of classifiers, so which classifier is doing better? We need to evaluate the performance of every classifier, and then we need to compare, and finally we can come to conclusion. We can decide that which classifier is optimal, which classifier is best for this particular purpose. So coming back to the different four phases. Phase A, if you look at, this is the feature extraction for MI task. What is MI task? Is motor imagery. Whenever the person is involved in motory task, what kind of impression is created in the brain, and how does the extraction get the signal in the form of EEG, and then the feature extraction is over. We extract the features. Those features are subjected to feature ranking and selection. We provide ranking to different features. Why do we rank? So that highly ranked features can be chosen and lower ranked features can be ignored. So therefore it goes to selection of features. And then we use, say there is one method which was actually used for this method called as binary harmony search optimization. That is binary harmony search optimization method. So in phase A, this method was used. In phase B, you look at here, this is actually on channel selection. The first one is feature extraction and then selection. Second major task it was on channel selection. And for channel selection, there is a popular method called as binary Jaya optimization method that was used. We will see the flow diagram of all these methods because this lecture today is highlighting the practical work, which is very recently over, has been over. So feature extraction, feature selection using binary. So what is important is the feature channel selection is by binary Jaya optimization. Once we select the appropriate channels, then we need to extract the features. So the feature extraction and selection is done by you look at here, there is another method called as binary TLBO. TLBO is teacher learner based optimization method. Teacher learner based. We will understand in coming slides what do we mean by and how does it how does this method work called as TLBO. Then the third stage is application of the algorithm which has been tested for channel and feature selection, and then we apply those data after optimization to assess working memory. And then is there any attention deficient? Is there any attention deficit disorder is there, hyper disorder is there, something kind of thing. This application is also included in this lecture. And then we evaluate all those methods, and finally we classify the methods and we evaluate the performance. And the last stage is statistical analysis of cognitive states of human brain. What different states of cognitive ability they are assessed with the help of statistical analysis. So this gives a complete plan of the work. So let's begin with first task. The first task in this work was improved motor imagery classification. Motor imagery classification was improved using the method distinctive feature extraction and selection technique. So how did we do this? How the method worked? MI task classification is actually very popular, that differentiating between motor imagery task, but it is equally challenging due to variable subject. As I told you that this kind of study is very much subjective. It can vary from subject to subject. I have already told you what do we mean by subject in the study of medical science or biomedical application or VCI. And then there are a number of task varieties. What is the task where a person is involved? If the task is changing, probably the classified output might change. So that is another problem. So classification is actually a challenging task due to varying subjects and also a number of or variety of tasks which are handled by the subject. So time and what kind of features are generally popular and used in the analysis of this classification and cognitive workload. Time domain and frequency domain features are very popular, especially in EEG signal analysis, and therefore and that need to be carefully analyzed so that we can get better performance in the classified output. So when the task is performed, any task which is coming from a variety of tasks, whenever a task is performed, what will happen? Some a specific frequency dominates other frequencies. We know that alpha, beta, gamma, theta, beta are there, delta are there. So a particular frequency will always dominate related to a task. Means all the frequencies will not be present equally in a certain task related to cognitive ability, maybe critical thinking or recalling, more stress or something like that. So in all such activities, some of the frequency will be dominating and few are less important and have major impact on degraded classification of performance. So to select the best possible feature set, we need to use certain optimization technique. And interestingly, as has already been mentioned in previous slide, very less explored for MI task classification. So we are interested in the MI task classification. What kind of motory task is there for which cognitive assessment is being done? So for such kind of work, very less amount of optimization technique has been, and that too highlighting a frequency feature optimization has been attempted. So the method one for the motor imagery task classification, the method one is feature ranking method. Remember what we are doing is improved classification using distinctive feature selection technique. For this task, the method one is feature ranking method, because I told you we are going to rank, we are going to assign all the features, we are going to assign ranks to all the features so that higher ranked features can be chosen and lower ranked can be ignored. So feature ranking methods for subband and relative power features in motor imagery task classification. So this was the description of data set. This was also published in one of the Journal of Healthcare Engineering in 21, this particular title. So number of subjects were 10. Number of trials each subject went was 20 and the number of runs was 8. The type of data was EEG, sampling rate was 512 hertz. What kind of task was involved while testing the feature ranking method? Movement of right hand and feet. I'm telling you, when something, when a subject is moving, how much is the workload in the cognition, cognitive assessment, that is our interest. So what type of task was involved? The movement of right hand and right feet was only involved. So then how did it work? The work is very simple. Look at here, data set. We got the data set, we imported the EEG signal and we pre-processed, then extraction took place. We extracted, some power spectral density and other features, and then we ranked those features. After ranking those features, it was sent for the classifiers, and there are different classifiers which were tested: random forest, QSVM, fine KNN, that is what is called as a k nearest neighbor, and the tree method. SVM is support vector machine. So then after classifying, the performance was evaluated, which classifier is working better for the optimal feature set, and then comparative analysis was done. How comparative analysis was done? Over the same data set, some other papers were found, other works were reported, and that set of existing techniques was compared with the proposed method. What was the proposed method? We use some feature ranking method. So this is a diagram. So the feature matrix which we obtained are represented by from A11 to A112. There were different features where 11 to 14 denote average PSD. Let us understand what kind of features were extracted in this work. So A11 to A14 where average power spectral density of alpha, beta, gamma and delta band. You all know about these waves. We have already given enough background in the previous lectures. Whereas A15, 16 and 17, look at here, that denote relative PSD of alpha to beta, relative power spectral density, alpha to beta, alpha to gamma, alpha to delta. That is a comparative alpha with respect to beta, alpha with respect to gamma, alpha with respect to delta band. And similarly, 18, 19 and 110, 11 and 12, that indicate varied PSD of alpha, beta, gamma and delta band respectively when there is a variation. So methods, since we are talking about feature ranking, what are the methods which were tested? See, you are talking about, you have an interest in AI ML. So I think AI ML is nothing but, we try to, make our computing device, we try to make our machine or computer intelligent as human being. How do we do that? We train our machine, we train our computer with the help of some suitable model, some suitable algorithm, some suitable mathematical equations. So here AI and ML has already started coming into the role. So mutual information method, chi-square method and correlation method. These three methods were used for feature ranking to rank a particular feature set. So I have included the partial result of all the methods used for feature ranking. You look at, these are the 10 subjects, subject 1 to 10, and then we took the average value of classification accuracy when we classified and which feature is going to be, a better feature. So tree method, the maximum one was 92% for this subject. Then fine KNN, weighted KNN, quadratic SVM, QSVM, a random forest. So you can see that the maximum and minimum are there, and the average value is also calculated. So average is resulted maximum for weighted KNN. So these all classifiers actually assisted us in selecting the best possible features in our method. So these selected features which were chosen, they were based on feature ranking method. So as I told you, mutual information method, chi-square method and correlation method, these methods were used in order to, choose the best possible features. So you look at here, the number of features, if you remember in the previous slide, number of features are included 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All these features are included. So you see here, what are those feature numbers which were which got certain priority. If you see the the vertical axis of the plot, a number of features, occurrence of selected features, and here is a feature number. The feature number is a very simple, you have seen in the previous slide. So this is how many times the occurrence was there, and accordingly the number was assigned, and the different methods are ranking the different features in different way. So whichever feature ranking was more, whichever feature ranking was more, that was chosen by this particular method. So then the results of different classifiers. Now again, what did we do? We selected the features, all those features, and then use the classifiers for all those 10 subjects. So you look at here, accuracy with all the features. What is interesting is, please try to understand. When we computed the classification accuracy considering all the features, without ranking, without choosing suitable features. So this was the percentage. Look at here, but accuracy without relative PSD feature. So we ignored relative PSD feature. If you go back, you know the relative PSD features are relative based features are A15 to A17. So we ignored three features. We found that 94.9 was the accuracy, 93 in case of this, 93.3. So everywhere the accuracy has been increased. Probably this these three features were not needed, and therefore they did not get good ranking. So they were ignored, and therefore the relative PSD features, removal or ignoring those features resulted higher accuracy. The second one is accuracy with best features from mutual information method. Means we used mutual information method for channel feature ranking and feature selection, and this is how we got the accuracy value. The somewhere in most of the cases the improvement is there. Somewhere we reduce. There has been reduction also, but in few cases there has been increase, but the increase is not significant. Accuracy with the best features from chi-square method. So look at here how much improvement or decay is there. So here also we recorded some improvement in few cases. Accuracy with the dropping out correlated features that produced this kind of ranking. So this helped in ignoring the features which don't have much dominance in the analysis and the further classification of the next stage. So this is the method all about. So this gives a comparison of all those classifiers with the standard classifiers, like all those classifiers are compared for the selected features, and accuracy has been highlighted. So this is a change in accuracy with using feature ranking algorithm. This is the number of features we used, and this side, is the accuracy. So you look at there, without feature ranking and mutual information method was used, chi-square method was used, correlation method was used. So you can see, say the accuracy plot. So accuracy plot says that when you are going for mutual information, there is reduction. But when we go for chi-square, it is increasing. But correlation method, there is a lot of decrease is there. Similarly, the features, the number of features, equivalently, the number of features was reduced to so much extent for mutual information, slightly, further reduced for chi-square, but in comparison with the reduction in number of features, the increase in accuracy is very good. And similarly, there is, slight decrease in the features by using the correlation method, but the accuracy is reducing so much. So here one can recommend that the chi-square method is working very well. That could be used in order to select, in order to rank, in order to assign ranking to all the features which are extracted. We have already talked about what are the features like PSD, relative PSD, and other features are there in this chart. So summary of the first task, first method of first task, overall accuracy obtained was 93.5%. And this was found consistent for almost all subjects like other approaches. In other approaches, the accuracy was varying, but this was found in the chi-square where it was almost consistent. And the analysis also indicates that the combination of features that has a capability and trade-off between accuracy and complexity of feature space means when you are getting more accuracy, the complexity of feature is has to be compromised. Filter methods suffer from a problem of stability and correlation. There are filter methods also, but that suffers with the problem of stability and correlation. So the next method for the same work, the task is same. What is the task? Motor imagery task classification. Remember, we are talking about motor imagery task, and you can again go back in the beginning of the slide. You can, because you may not reconnect that why we are talking about MI task, MI task. If you remember in the beginning, I told you motor imagery, attention, memory, cognitive ability. These are the tasks which are related to cognitive workload. So we are still working, still discussing on motor imagery task where you perform certain motory task and how does the brain respond to certain motory task. That is the discussion we are doing. So look at this. You see here this particular work was published in IEEE Sensor Journal. This is a very reputed journal in the area of sensors. So IEEE Sensor Journal, it was published in 21, probably year 2020 by of course my scholar and us. So this is a flow diagram of method where the name of method is subband statistical wavelet. The method was statistical wavelet was used. So obviously statistical wavelet features will be extracted. Then which method was used for feature selection technique? This method is also for optimal feature selection. Remember, the previous work was on feature ranking. This work is on feature selection. And what is the name of method? Harmony search is a popular name. Harmony search optimization method to select the appropriate features for motor imagery task. So this is the flow diagram. The first stage is data acquisition and pre-processing, where EEG signal repository is there. From there, we got the EEG signals, and then we acquire, we pre-process, we segmented the data set. And why we segmented? Because we wanted to decompose all the signals into different subbands. So therefore, there is a term coming as a subband. What are the subbands? Alpha, beta, gamma, delta, and theta. These are the subbands which have been segmented from the main signal. Then discrete wavelet coefficients were calculated. Then statistical features were calculated from DWT. And then we created the feature vector. I have explained in the previous lecture. When you have features, you create some feature vectors, matrices. You can't just, use the features, the huge amount of features in the work. So we arrange in a particular manner called as vectors. So that then goes to harmony search optimization based feature selection, where this method is used to select suitable number of features, and that then goes to classifier. So the first stage is data acquisition and pre-processing. Second stage is feature extraction and feature selection using optimization method. And then the third stage is, you see we are using classifier, and then also we are evaluating the performance. So the third stage under method 2 is MI classification, that is a motor imagery classification and its evaluation. So what are the methods which were tested in this work as classifiers? Complex tree method, fine KNN method, weighted KNN method, back tree method, subspace KNN method. So remember, these are not, very new methods. These are all popular methods which are available as a classifiers we can use for our task. So as I have already told you in the beginning, a lot of classifiers have not been tested, especially for cognitive workload assessment kind of research. So we tested number of methods and we found that all these methods were not used in all the research papers which are available, till today. So MI task, what was the MI task? Hand movement and feet movement, and the classification performance evaluation was done, and then it resulted the comparative analysis. So this table gives you the, some comparison results of beta and gamma. These are only related to beta and gamma DWT features, discrete wavelet transform features for MI task classification. So you see if there are 10 subjects, complex tree resulted this kind of accuracy, classification accuracy, fine KNN, weighted KNN, backed KNN, and subspace KNN. So we got the different average values, and this is that AU curve that also determines which method is the optimal method where you found, and this method was considered as a good approach for the next stage. So precision recall and F score are actually used in order to plot the ROC curve and other plots in order to assess the performance. So these are the values for the different subjects in terms of precision recall and F1 score. So how does yeah, or how did optimization impact the performance of classifier? Impact of optimization for feature selection on classification performance. So you see here accuracy is given weight before and after. So the colored one is accuracy before optimization, and the black one is optimization accuracy, means accuracy after optimization. So if you see that for all the subjects very carefully, if you look at the subjects which participated in the study, for all the subjects, look at when we used optimization method, the classification accuracy was increased in all the cases. So this is impact or importance of the optimization. The meaning is very simple. If we have used optimization method for feature selection, that is actually helping in improved performance, especially in terms of increased classification accuracy. That is very important. So we are getting two advantages, two benefits. One, our classification performance, we are not getting any loss, rather we are getting improvement. Number two, if we are reducing the feature vector, reducing the feature set before sending them to the classifiers, so computational complexity, unnecessarily more computation would have been required. That is getting reduced. So that is a bigger advantage. So there are two advantages. So this gives, the combination of different methods, linear discriminant, RF, all those methods are there, which have been tested and comparison was done. So for four subjects, wavelet feature, PCA, principal component analysis, and then feature selection, then proposed SWT, proposed feature selection. In all these cases, the accuracy was found very high. Motor, so let us sum up about this task, that is a statistical wavelet method and harmony search optimization method for feature selection. So motor imagery classification was done using, we only utilize beta and gamma. So beta and gamma could help us in assessment of motor imagery task. And so we used only two subbands, beta and gamma, and other waveforms did not contain much information or did not change much when there was a motoric task related to movement of our right hand and the right feet. That is the something. So the features were found very efficient for classification of motor imagery task than alpha beta frequency based features. Wavelet coefficients of choice of frequency band extracted and further statistical properties were calculated from the coefficients, and then features which were found finally after optimization that helps to outperform, helps the system or method to outperform as compared to statistical features. Feature selection method you have seen that also helped us in improving the classification accuracy, and which one was better? It was there in the previous table called as weighted KNN. DWT features of gamma frequency actually has a good impact in motor imagery classification task. And there is one more method called as wrapper method for feature selection was found suitable for classifier due to limited number of features. and improve involvement of all the features to create subset rather than manually ranking selection. So the harmonic search optimization, that was the main method in this task, was used in the study, provided good results. However, the method required parameter tuning, the fine parameter tuning of the parameters of the training, that becomes challenging to due to challenging to achieve good convergence. When the method will converge, it depends on the parameter tuning. So that parameter tuning was challenging task in this particular method. So going to the next task, the task is under task one, you have seen there were two methods. One was feature ranking, second one was the feature selection. The second task of the cognitive workload is efficient channel selection. Look at here. In the previous work, we did not work on channel selection. So in this task, channel selection and feature selection approaches are used so that both of them could help us in getting better assessment of cognitive workload. Right. So you may think that working on channel selection, working on feature selection, does it impact in the BCI application? Of course, BCI application hugely depends on the biomedical signals, physiological signals, and when you are involving huge amount of data coming from all the channels, then huge amount of features coming from all the feature sets, and then your complexity is going to be very high, and your the timing, especially in BCI, remember brain computer interface, what is very important in BCI is response time. It's very simple, you can understand. If I'm using BCI for to help a person in the assistive technology, and the BCI is responding very slow. So the person who is getting benefit of BCI is not getting the actual benefit. He is getting, but so much delay is there. And therefore, time is very important thing. And therefore, remember when we are talking about the work like feature selection or channel selection, it has a significance and relevance in all the applications of BCI and the cognitive science. So in particular, in this work, both are playing very important role. That is feature selection as well as channel selection for cognitive workload assessment. In the assessment of memory, utilization of memory, in the assessment of doing some motoric tasks, and the assessment of even brain disorder and disability. We also try to use these results in that application as well. Probably I have included that discussion at the end of this lecture. So EEG signal is one of the easiest ways of brain monitored by using latest devices. You all know we have had a lot of discussion on different modalities. We have found that EEG is most popularly used because of a number of factors. The biggest factor is easy to use, portable, and thirdly, which is even more important, is non-invasiveness. There is no risk at all. Meta-heuristic optimization, called as a method, is very popular, used for variety of categorization of EEG signal tasks and the analysis, but is still not very popular in the area. So look at what is the research scope for us in this work. The meta-heuristic optimization is a method where heuristic parameters are there, meta-heuristic approach is there. So that has not been actually tested for cognitive workload assessment in existing literature. Much work has not been done. So we have actually used meta-heuristic model for channel selection and feature selection for cognitive workload assessment. So what are those algorithms under meta-heuristic models? We will discuss in coming slides. So there is a method called as LJA, L for logical. So if you can search the method, Jaya optimization based method is a very popular method. Mostly, this method was introduced by a mechanical engineering professor for optimizing some task related to some mechanical engineering or mechanical engineering based applications. So this method was not very much tested for such application working on EEG signal. So LJA method, logical Jaya, means we did not use the Jaya optimization method, originally as it is. We actually modified and we made it logical Jaya. And this approach was used for channel selection, and happily it provided good performance improvement for a cognitive workload assessment. And there was another method called as binary chaotic Jaya optimization for cognitive state assessment is there, which we used in the work. There is another method which has been implemented. I'm going to discuss about all these three. So in the beginning, some of you guys were very much interested that we want to understand the role of AI in the area of cognitive science in the study of brain computer interface. So you can see that these are your AI methods, ML methods, optimization methods, which are, playing a very important role. I'm talking about the work of my PhD scholar. I mean, you can find her publication. She got very good publication. I think two to three, very good publications in IEEE sensor journals, one or two papers in elsewhere, journals. So it got really, it created good impact in terms of publication as well, and visibility. So the reason is very simple, that these methods are AI ML based methods which were not much attempted in the area of cognitive workload. So the third one is a automatic cognitive workload assessment with the, using logical. I was telling you in the beginning in the block diagram, you have seen TLBO, teaching learning. You can also say teacher learner, teaching learning based optimization, very popularly abbreviated as TLBO, teaching learning based optimization method. So this method is also a method used for optimization task. But again, what we implemented is modified TLBO called as logical TLBO. Like logical Jaya, we used logical TLBO. And there was one more method for ranking different methods. Remember, we can use a number of optimization methods, but finally we have to rank all those methods, that each method is working, how each method is working. We have to choose that method which is working very good. So Promethi, preferential ranking based method is a multi-criteria decision making approach, was used for ranking of different algorithms. So I have included the results of this method also in the coming slides. So this was the data set over this particular task was tested. The number of subjects was little high, 48. The age group was 18 to 23, and simultaneous capacity test module was a test conducted. Emotive Epoch EEG headset. The device was used to capture the signal, and number of channels used in this data set in creating the data set was 14. So what kind of classification was done? I'm talking about cognitive workload classification. So two classes, either the person is doing no task or doing some task. So it's called as binary classification. No task or doing some task. And multitask means if a person is involved in a task, say any task, using either motory task or thinking something. So any kind of cognitive workload. So the task where the subject is involved, what level of task, whether it is a low level, medium level, high level of task. So low, medium, and high workload assessment was the output of classifier based on this data set. So this is very interesting work, I tell you, where the work was, for optimization of the workload, and also the different methods were evaluated in terms of their ranking. So we have already discussed about channel and feature selection. So coming to the method one under this task is LJA. If you remember, I was talking about logical JA. So logical JA optimization based channel selection approach for performance improvement of cognitive workload assessment. Correct. So in unlike previous lectures, today I'm talking about more mathematics, more results, more discussion, because this is a practical work. In previous lectures, we were discussing about theoretically, the fundamentals, the concept of those topic, and how fundamentally, conceptually, the theory is used in order to develop and design different types of BCI systems. How do we acquire EEG signal? How do we analyze? How do we classify? How do we pre-process? How do we use signal processing? But here, actually, this is an application of all those which we have studied in which we have covered in the previous lectures. So what is the need and what was done? The need was the channel selection is generally the binary optimization problem. You either select the channel or you don't select the channel, and eliminate the need of parameter tuning. If you remember in the previous task, there was a big challenge related to parameter tuning. So the parameter tuning has to be eliminated. That needs to be eliminated, and selection of that curves which are sharp curves for binarization has also to be eliminated, so that rather than binary optimization problem, we can convert to logical optimization. So original population update is a the optimization where what do we do? The weight or your population or a population of sample, sometime in a neural network kind of thing. There are different layers where each node has a weight. So weight always gets updated. So original population update for Java optimization method was this. This was actually there in the original paper. If you search the original J optimization method, you will find how the next population is, updated by using this formula. But here what we have done, we have made it logical. Why we are calling it as a logical? You can see that the logical operators are used, like exclusive or operators are used. And this was also published in one of the Science and Citation Index journal, Electronics Letters in 2020. This particular LJA method was also published. This is a flow diagram of the method that we imported the data set. We initialize the population size, number of features, and then converging criteria where the method will converge. And then we generated the set of population randomly. We calculated the fitness for best and worst solution. And then we kept on modifying the solution based on, using the J optimization. So it is the solution better or not? If it is yes, so we accepted and replaced the previous solution. If it is no, we went to the previous solution. We again, tested the termination criteria, and then we found fine. And when the termination, the convergence criteria is met, because those who study classifiers or those who know about classifiers, classifier will start, what I can say, will stop working when it meets the convergence criteria. What is that minimum error? What is that minimum threshold where it reaches and then it will stop? So that is what is termination criteria. If it stops, then we finally get the optimal features. So this is one comparison of LGA. You see here for two class and for multi-class. For two class, we did not find PSD features accuracy in terms of that. We did not get any such work. And for multi-class, the accuracy was 69%. And without optimization, we got in some work 91. No, in fact, we tested without using optimization. So it was found 91.1% for two class, binary class classification. The person is doing task or person is not doing a task. And it was 73.3% for multi-class. The level of, engagement, low level of workload or high level of workload or medium level of workload, how much workload one is having. So here also improvement you can see, in terms of PSD. And when the proposed method was used, what was the proposed method? Proposed method was LJA. Then you can see that for binary task, it was 100%, means it was clearly, providing the result whether it is a no task or task. But in case of multi-class, the percentage was 91.27%. But this is also very good percentage of classification accuracy that you can see in the result. And this is another way of, comparison here. If we know about the training and testing process in the optimization and the ML method, you always have some test sample. So this test size or test sample, this zero point 0.2, zero point 0.3, zero point 0.4, zero point 0.5. So 20% of the total sample we take as a test sample here, 30%, 40%, 50, 60, 70, 80, and 90%. So this is the test size or sample. And look at the plot. The plot is representing or depicting the accuracy for binary Jaya, and then harmony search, particle swarm optimization, and proposed LJA. So binary Jaya is still inside, but there is definitely improvement. Binary Jaya resulted around 95%, and that too for 90% of the test size. For 80%, it is little less, for 70% less, and it actually reached to 100% for the different test sizes when you go for, proposed algebra. So this was a wonderful method, and this is the convergence curve. Which method converges? How does it converge? So logical Jaya convergence is this one. The convergence accuracy is this one, and binary Jaya is this one, and green color is this one. So this is the convergence accuracy. How fast one converges is very important. How fast one converges, how fast one gets, stability, and that is very, very important. So this is another way of channel selection. This is the result for channel selection. About this is a nose area and this is opposite area. These are the two ear lobes. So how much percentage of channel selections were made, and how feature channel selections were channel how how much percentage of channel selection was done? This is indicated by this diagram. Probably it has a lot of description. I have not included the complete description of this. And in fact, I do not have much knowledge about, this particular diagram, but this is indicating the percentage of feature selection, that impacted this classification accuracy. So summing up about the LJA method, it was evaluated for the data set and compared with PSO and harmony search and binary Jaya method. And then method not only provides good accuracy, but also converges very fast. The converging is very fast than other methods, and for both the two class as well as multi-class, cognitive workload problem. The convergence is achieved at less than 10 iterations. And remember, in all our optimization methods, iteration also plays an important role. So even the convergence was achieved in less than 10 iterations as compared to other method for two class, and for multi-class, not only convergence is achieved. So it was not only less number of iterations, but also the fast convergence which was achieved. So effective channel visualization and its effective accurate channel selection. So in the previous map kind of picture, you could see channel visualization and its effective selection. It was used to automate the subjective models and helps the psychologist to understand the brain disorders and disability. So this particular work can help really the psychologist to understand where is and how much impact is there in which exactly which part of the channel, which part of the brain, and accordingly channel can be given priority. So the other method is binary chaotic Jaya optimization for cognitive workload method. Before I move to next method, I want to ask you if you have, any queries. If you want to interrupt me, feel free to interrupt me. It's not one way, traffic. There must be traffic from other side. I have to keep in mind that something is coming from that side. I have to be, I have to drive very carefully. So if you feel anytime something is there which requires more clarification, or you want more description, you can always, or you want something to be repeated, you can always interrupt me. Or of course during the break, once we are back after the break, that time you can always ask me. So the other method was a binary chaotic J optimization, and for same cognitive, it's not for cognitive workload, but cognitive state assessment. There was a objective function in all the classifier. There must be objective function, and when the objective function is the role, the objective function, the aim is always to minimize the objective function. So here it was accuracy, and the feature selection, as we have noted, is a binary, like channel selection is a binary optimization problem. So original J optimization method for continuous optimization problem was converted into binary optimization algorithm by using these, these equations. And then some chaotic number generation was used in this method, and this was published in one IEEE conference in 21. So this is a comparison of all the classifiers using this method. And you can see there are different values which are resulted for the different methods. And for different test sizes like 20%, 30%, and 30%, the convergence curve can be seen. I think last two diagrams are just repeating. So just one and second are very important. So you can see that which method is converging fast, and for which sample, and how does this test size matter for convergence, you can understand. So the idea is, you have some comparative analysis of different classifiers, different models, AI models, which can be used for different applications where you are using EEG signal. Before using EEG signal, recommendation is, go for optimization for both channel selection as well as feature selection. So this particular task, rather the work is on workload assessment, but same can be done for, even we are talking about motor imagery task, remember. So even if some command is generated, to perform a task, to control robot or to control robotic arm or to control a wheelchair. Of course, there is an interface. Here we are not talking about the brain interface, but in brain interface also, if we are controlling some device, controlling some robot or controlling some wheelchair, there also you can definitely, use such, you can test such models to reduce the number of features and the number of channels so that you get the optimal performance in the task where you are interested to use the brain computer interface that is there. Probably the third diagram is also the different diagram, but probably the test size is different. So we can see that. I'll see also and I'll try to correct. Yeah. So this is performance evaluation. A green color is accuracy. This red looking color is a convergence. And where is this one? Where this side, I think the number of features are there. Yeah, this one, this yellow color. So look at here that green color is accuracy. So without feature ranking and with feature ranking. Without feature ranking is this one with 100%. And in here, this was reduced. Here again, it was reduced. And the features, number of features is reducing in the cases. So in this manner, you can evaluate the performance of the different methods, and you can accordingly use it. So this is a comparison of a proposed chaotic Jaya, and you can see that proposed chaotic Jaya resulted highest accuracy. Of course, there is a logical TLBO also that resulted 100%, but both have their advantages and disadvantages. There was, I think we are going to talk about TLBO. Then you will understand that TLBO has some limitation, and especially in cognitive state assessment. So we'll see when we go to the TLBA in the coming slide. So let's sum up. To solve the problem of dimensionality, there is a huge dimensionality related to feature. The chaotic method based binary feature selection model was used, and it does not only improve the accuracy but also selects the relevant features. By the way, yeah, this is what we have been talking about. The number of relevant features is reduced, and at the same time, we are getting the better accuracy. So without feature selection, this is the accuracy. With feature selection, then accuracy came up to reached up to 96.11%. So this was already given in the plot. No need to repeat. So the approach provides maximum accuracy and converges at least a number of iterations. So lesser number of iterations was also there. How much reduction was there in the number of features? Almost 60% reduction was there. And this is so interesting, This is so exciting. I mean, the number of features, the burden is reduced by 60% to the extent of 60%, and that too with the improved, sorry, classification accuracy. That is very interesting. So let's talk about this one, then we'll have a break for some time. So method three is the automatic cognitive workload assessment using logical TLBO, what is called as teaching learning based optimization, and Prometheus for ranking. So two methods are basically used here. One is a ranking up method, second is a optimization method. So you can see we are again using the data set data storage for EEG signal. This was also in another, volume of IEEE sensor journal. Two class cognitive workload data, multi-class cognitive workload data, we got it. We extracted the raw signal, then we used some pre-processing, we extracted the features, statistical wavelet features were extracted. Then we selected suitable features using TLBO and then classification. After classification, the methods which were used for classification were ranked by using Prometheus method. So for both two-class cognitive workload assessment and for multi-class cognitive workload assessment, we compared all the methods and we provided the ranking to all the methods. So this is how the original equations in teacher-learner phase are there, and updated equations which were some modification was done in the fitness function and in the learning parameters. 10H function is not there, but we are using 10H function in the difference in the calculation of mean value, which is fitness function. So we tested different methods, we got good results, and that too for the cognitive workload assessment application, which for which it was not tested actually in the previous or existing work. So this is the name is very simple, teacher learner based. So say there is a teacher in the class and 10 students are attending the course. So if the students are not performing, how to improve the performance? Either the learner can improve, learner can align to the teacher, learner can update his knowledge, learner can change himself or herself, and then learning impact will take place, learning outcome will come. Or teacher can also align to the needs of the learners, and the performance could be improved. So this is the logic, teaching learning based, teacher learner based, where both have to contribute in order to get good result, good learning outcome. That is the idea. So this is actually, since the block diagram was, or the flow diagram was very big one, so still I believe that you are able to read the text which are inside the boxes. So we started with initializing the population and termination criteria. It is nothing but the convergence criteria. So you look at the block diagram, we have identified this particular block as a teaching phase or teacher's phase, and the other part is assigned as a learner's phase. So calculate the mean of each design variable with which we started, calculate fitness function and identify the base solution, modify the solutions based on equation 1 and 2, which are included in the previous slide, like here. And then, is the new solution better than existing? Teacher is assessing whether I have modified something, I have changed myself, I have changed the teaching learning methodology, how teacher will improve his result in a particular course. He can try modifying the teaching learning methodology, teaching learning pedagogy. He can modify, he can improve the quality of teaching learning materials and so on. So doing so, is there any improvement? If it is yes, it will go to the learner phase. If it is no, then it will be rejected. I mean, it is not working. If it is yes, then very good. So let learners also contribute. So the learners will also be doing based on some design parameters, and they will be also checking whether it is better or not. If it is not better, it will modify. If there is modification, it will be accepted. If there is not modification, it will be rejected. If it is accepted, so it will finally check the termination criteria, whether the convergence, otherwise it will keep on working. So you have to check the termination criteria. Otherwise, termination criteria is not met. Look at here. It is again going back and checking the mean value of each design variable. So this is really very interesting, flow diagram. I believe all the titles which I am reading today, all the papers because I'll be sending PDF of this paper after PDF of this lecture after this lecture. You can search those papers which are available in the IEEE library. You can open those papers and study those papers. You can also take that as an optional assignment. I would be glad if you read those papers of our own team published in IEEE Sensor Journal and other journals. And if you have some, queries or some enthusiastic interest, then we'll be, glad to respond. I can also connect you guys with my, PhD candidate who has been recently awarded her doctoral degree. So this is a comparison of result. Look at the comparison very interestingly. The first one is classification performance of two class. Two class means no class or class. And the next comparison is for multi-class. So multi-class cognitive workload assessment, and this is task versus no task. So what are the methods? Look at PSD with SVM model, the statistical wavelet with SVM model, statistical wavelet with WKNN, PSO, TLBA with sigmoid function. You know that there are, I'm really sorry. Sigmoid function and 10H functions are, the functions which are used in optimization and ML methods you are aware of. So TLBO using the sigmoid, TLBO using 10H function, then, goal probably, Wolf optimization, isn't it? Is GWO, and then logical TLBO. So what are the parameters which are compared? Accuracy, computational complexity, time of execution, and average convergence iteration. So if you see the accuracy, 100% accuracy was obtained for logical TLBO as well as TLBO with, means in all TLBO cases, you look at 100%. And computational complexity was also, reduced. It is medium. Of course, it is low in case of statistical wavelet. But what is problem with the statistical wavelet is accuracy is very low. And therefore, we want both the benefits. So you see here, accuracy is, 100% and it is medium. So this also is the, publication in one of the journal. I think we are doing the same thing. Yeah. So the next one is time of execution. How much time was there? So if you compare actually statistical wavelet with WKNN, so even the timing is the smallest, but the biggest challenge in this method was even though time required was very less, and accuracy, the computational complexity is also less, but the accuracy is actually almost half of what did we get here. But here the time of execution was little higher. Of course, we can have a compromise in terms of this one. So even if you can think about a TLBO with sigmoid, but the computational time was little more. But if you go for TLBO with 10H, the advantage is 100% accuracy, computational complexity is medium, and the timing of execution is also less. And what is interesting thing is average convergence iteration is also less. So we can decide which method is optimal for which kind of application. And remember, this is for task versus no task. But if we go for multitasking, where low amount of tasks, middle level task, or high amount of tasks someone is engaged, you will find a comparison in terms of accuracy, logical TLBO, in terms of complexity medium, time of execution here is 140, second, but here even those which are giving 100%, the timing is more. But here TLBO with 10H is also, requiring medium computational complexity, 100% accuracy. The time of execution is a little less, but the iteration is little, taking more time. Here the iteration convergence is fast. So all these factors are very important. So this gives a clarity of what are different models that could be used in order to assess the multi-class or binary class cognitive workload assessment. Of course, you might be wondering that we are working on these models just to assess the cognitive workload. So you have to keep in mind all these models are working with the reduced feature set and reduced channel set. And this is why we are seeing the advantage or benefit in all such tasks. So this is the optimization performance for two class, convergence for two class for different test sizes. This is for 20%, this for 30%, this for 40%, and accordingly, then you can interpret where you are getting fast, where you are getting convergence, early. You can understand and you can decide. This is for a multi-class workload. And if you actually see the plots are very different when you compare with the two class. So this is a comparison of all these methods. This is called a spider diagram where I have already tried to explain comparing in terms of the test size and the accuracy. So see the red color that is going to 100% for logical TLBO, and this is a feature selection algorithm which is good for a different size of multi-class. So is a comparison for multi-class workload assessment. And as I was telling you that cognitive, I'm sorry, that there are different methods and how to rank those methods. There was a method called as Prometheus was used, and it solves the problem of how to select the best method for multiple methods that are reaching to convergence. If they're all reaching to convergence and they're similar accuracy, similar timing, so how to rank them, which is better then? So that for that, Prometheus was used. So Prometheus ranking for two class, and it gives number of parameters, like accuracy, and then I think these are some scores. I have to check. These are the classification criteria. I mean, these are not true positive, true false positive, but these are the classification criteria. This is accuracy, of course. And in terms of those classification criteria, you look at the ranking for two class. Ranking for two class, the best rank is TLBO 10H. And for multi-class, logical TLBO is standing at the best position. And the ranking is highest. So for multi-class, recommended method is the logical TLBO. For binary class, recommended method is TLBO, ordinary TLBO with utilizing the 10H function. So let's sum up and close, and then we will start from the next part in the next lecture. So subband statistical features are extracted from EEG signal and all the 14 channels. Logical TLBO method was used, and we reduced the feature set and also got the early convergence. Different parameters like accuracy, convergence, execution time, number of tuning parameters. Actually, in the previous diagram, these are, I think, tuning parameters, and convergence, something, those parameters are there. I need to find out the full names, execution time, yeah, number of tuning parameters, they're all compared in the, and the approach is better. The least convergence time is needed, and feature reduction, the feature was almost reduced to half. So 50% reduction was there in the feature vector. And to differentiate different algorithm in terms of convergence curve, how a particular method is performing, Prometheus method was used for algorithm selection. The logical TLBO is the best method for multi-class we have seen, and in the binary class, in two class, ordinary TLBO with 10H was used. So the proposed method can be evaluated on different problems to generalize the model. So this is what I'm saying. What is the learning of this work? Why I'm talking about this practical work, but be, is that all these methods could be tested for other applications of BCI and cognitive science and EEG signal analysis. That now we are coming to the last stage of the work, last part of the work. Cognitive workload assessment, channel selection, feature selection, and then how the cognitive workload assessment was classified. Now coming to assessment of abilities. So empirical analysis of logical TLBO and JA has been done to evaluate the model for different applications of cognitive assessment, such as working memory, focused attention, and it helps us to get, to get a generalized approach for the model. And the technique may or may not work efficiently due to the problem of data variability and dimensionality of features. Selection of the initial sample in an optimization problem is always a challenging task because it impacts the convergence of the region. So empirical analysis was carried out on working memory and attention, and also for ADHD, attention deficit hyper deficit disorder, right? So for this method and empirical analysis was tested. So empirical analysis for LJA for different abilities, working memory and attention. The data set 86, 72 male, 14 female, and the average age was 19.75, actually 18 to 23. Duration of test, that is recording, was done for 40 minutes. Total time taken for all those subjects was 3 months. Remember, if you remember, I was telling you the biggest challenge in the BCI and cognitive science research where you need brain signal. Unlike, not unlike, like other medical imaging research where you want the data, medical data, biomedical data, persons, you need ethical committee clearance. You have to acquire the data, you have to get the sample. It is not very easy to encourage the people, encourage the subjects to come forward and provide the data for all these brain signal and other signal. So therefore, it takes time. So you can say in the research why only 86 persons, and that too they were requiring 3 months. So it's not easy task. Remember, it's always very difficult task. So average 3 subjects per day, it was only covered, and that is actually reality in a biomedical research. If you want to do something in BCI or biomedical cognitive science or in medical science research, this is the reality. So number of features which were calculated is 280. Number of classes for all those abilities, working memory and attention, low, medium, high cognitive ability. So there were 3 classes. And for attention, there was focused attention and perception and memory. So these 3 were the classes, and all these classes, I'm sorry, all these abilities, attention, which is focused attention, I'm paying attention, in concentrated way, and then I'm trying to perceive something, my perception ability and working memory, how I'm able to use my memory, in my current work, how I'm utilizing. So all these have been classified in 3 levels. Low, you can say low memory, medium memory, and high memory, like low attention, medium attention, and high attention. So this is the data set where we already got the data set for all these classes. What is important is how this optimization could assist in improving the performance of the cognitive ability assessment. So this is the diagram, importing the data set, taking population size, randomly generate set of population, calculating fitness function, modify the solution, updated JI equation, and if it is giving better, keep the previous solution, otherwise go back and change and just verify the criteria. So the flow diagram is not very different. What is important is the data set and the application. And the method was what method was used was LJ again for a different task. What is the task? The assessment of cognitive ability rather than cognitive workload. So accuracy using different ML approaches. You guys, some of you guys are very interested in AI, ML. So you can see that how ML models are, how do they perform? Say working memory, perception, focused attention. So for working memory, the classifier, the tree gives 47.2%, and then linear SVM 66.4%, and weighted KNN provides 69.8%. Perception, we want to calculate focused, attention or perception. So you look at the classification accuracy. You can understand what do we mean by classification accuracy, whether the attention was low, whether it is high, whether it is medium attention. So you see the, classification accuracy. So it's not very easy task to evaluate whether the person who is having some ability, cognitive ability, person is actually paying attention. So the amount of paying attention, whether it is a low, whether he is paying very good attention, whether it is a high, or whether the attention is average. So you see the performance accuracy is not very high for different models, tree model, fine KNN, weighted KNN, quadratic support vector machine, cubic SVM machine, and then linear SVM. So this is the reality, right? And then the classification of attention state, the number of features which were used as 139, and you look at the different performance of different methods and how many iterations were used, and the convergence curve for accuracy of focused attention is there, where you find TLBO 10H, this red color, and you see the red color coming this side vertically. So, the time you have to compare with others. So it's getting converged early. So this is how you can make inference. Classification for a state of working memory, the number of features involved were 144, and accordingly there is a comparison of convergence. And the empirical analysis for attention deficit I was talking about, data description for serious game-based EEG. The person who was, I can say the task was on game, but ADHD problem was there. So there were two categories of, patients, subjects, those who had ADHD, those who did not have. Number of subject only 8. Remember, when you find such person, such subject for your study, it's not easy task. You can say, and I also want to do in the area of cognitive workload and binary, BCI in my university. So what is the difficult thing is how to get such persons who are, suffering with ADHD. Many of them don't declare the problem is. So how will you know that the patients are coming forward and they are providing you the signal? So average age was, and you can also see even if a number of subject is 8, I have been telling you in the beginning, the problem of mental health, the seriousness of the mental health is actually in the adults. You look at the average, age group. Modality was EEG, and they were asked to focus on a gameplay in order to assess whether they are able to pay the attention. So duration of test was 2.5 minutes. Some game was, played, and they were asked to watch. Number of sessions was 10, features 9, number of classes only 2. What were the 2 classes? Whether ADHD subject or non-ADHD subject. The approach was very similar. What we used the approach as a general classifier for LJA. It's not very different. And this gives you the comparison for, you see ADHD versus non-ADHD. Look at the different classifiers, how they are performing, the classification accuracies in terms of ADHD or non-ADHD. So you can find 98.4 for fine KNN and 98.4 for weighted KNN. And when you compare on the focused EEG data set, we also evaluated our method. What was our method? All logical JA, logical TLBO. So logical JA you see here for a focused EEG data set, accuracy was found 99.46. For EEG data set, logical TLBO provided 99.4. So you can see that even if you compare with other methods, and in one of the method, we also found they have used functional MRI, right? So the accuracy of the classifier was 86.55%. But here, using this logical JA and logical TLBO methods, you could see even in this cognitive ability, why we are saying this is example of cognitive ability. Attention deficit means what? You don't have ability to pay attention. So this is our cognitive ability. Working memory means I am not able to recall properly. I'm not able to memorize properly. I'm not able to, recollect properly. So it's working memory. So this is my ability, right? Paying attention is my ability. Focused attention is my ability. Attention deficit means there is some problem in the ability. So therefore, this is actually, I can tell you, very interesting work that how the cognitive workload, is evaluated, and then how cognitive ability is evaluated. How can we, I can say, classify the different abilities. And then you can ask me a question, Professor, then once you are classifying, then what is the need of this classifications finally? What is the use of this? The use of this classification is obviously you can understand once you know that this much deficit is there. This is the level of ADHD. This is the level of poor attention. This is the level of, poor working memory. So you can then recommend those subjects for rehabilitation or, some kind of diagnosis you can recommend. They can go and then go for the treatment. So this kind of analysis actually helps in detection of the different disabilities at early stage. The problem is you have seen when we are working with the cognitive workload, they are moving hand or feet, we are getting more number of subjects. But the real time challenge, working with the cognitive abilities, the number of subject in the database, you see there are only 8. So that is actually, is really challenging task in this work. So this is a comparison of all these methods related to ADHD. I mean, the red colored is a logical TLBO. So after certain number of iterations, it is outperforming all the methods in terms of accuracy, in terms of especially while classifying the cases of whether the cases are ADHD or DHD. So let's sum up. LJI and LTLBO are providing highest accuracy in this type of application where we are classifying the cognitive abilities. Convergence is lesser than 10, less than 15 as compared to other methods. So local minima is not getting into it. Means it's not stuck and it is getting converged, and that too with a lesser number of iterations. And then focused game play can be combined with proposed optimization technique for ADHD patients. And then conclusion finally about this entire presentation. Practical work is feature selection, channel selection. They always improve the motor imagery classification, relative PSD features and their variants are characteristics of motor imagery task for better categorization. Algea provides better accuracy and converges even very faster than other methods for both two class as well as binary class as well as multi-class cognitive workload problems. And in binary chaotic JA for feature selection, accuracy was improved up to 96%. We have seen logical operators using TLBO becoming logical TLBO. It outperforms all the existing methods in terms of accuracy for all different test samples, test sizes. The method reduces. We have seen the feature dimension up to almost half. So 50% reduction is a considerable reduction. And then Prometheus also helps in when the methods are all converging, because they're all converging means they're all doing well, but how they are converging, how fast they are converging. So there was a ranking method that was also implemented in order to provide the ranking to different methods, and that was also really well. So what is the future direction? In current work, meta-heuristic techniques were used, and all those techniques were used on the set of subjects for similar group. Means there was no dissimilarity. If the people are all from ADHD, DSD, so the study was on same group. This can be further evaluated in case of inter-subject variability, person to person variance. Then study was based on single objective optimization of maximizing the accuracy. However, in future, we can also think of research for multi-objective optimization. Means your objective function, fitness function may be many, and we can aim at achieving the fitness function to minimum value for all those multiple values for different aspects. And of course, considering the different aspect along with feature accuracy trade-off. The study can be extended toward multimodal analysis of cognitive assessment using meta-heuristic technique. The proposed approach needs to be tested in what is very important is real-time environment. It means if you have a cap for EEG, get the EEG, and just find out what is the cognitive workload, how much is the workload, how much is the ability. So working in real time is always a challenging task. All those work which are there, even my PhD scholar who has done this work was on the data set which is available. But working in real time, capturing the EEG in real time and analyzing it, signal processing, applying signal processing, extracting the features, training it, classifying it, and resulting some analysis, say in terms of cognitive workload and ability is a real-time challenge. So real-time environment is actually a great future research direction in this area. So more work has to be or needs to be done to investigate complex paradigms and robust ML approaches. Robust ML approaches means, I mean, we need to develop a framework of ML models, ML methods, those which could be used for, these tasks in a robust way. I mean, you have seen that one method was doing better in terms of accuracy, other was doing better in terms of timing complexity. So let's have some framework of methods, robust ML approaches that can provide us better accuracy with reduced time complexity, with reduced sample size, and so on. So that is very interesting thing that is the future direction of the research work. So this completes, the the discussion about the cognitive workload assessment, assessment of cognitive ability. And if you remember in my last lecture, something was pending related to ethical issues. But we are talking about EEG signal processing. So this is not new and this is very much relevant to this topic also. So let's complete that in this particular lecture. Ethical issues. Whenever, there is ethics involved, access to brain and disorder, when you are asking the subjects persons to come forward and get the data. So there are ethical issues involved, engaging the attention and affecting the action of scientists, clinicians, and policymakers. So at all level, how can you work on a biomedical signal of a person? You need ethical clearance. Is it ethical or not? There are a lot of discussions going on. The principles we have to always keep in mind working on EEG signal or brain signal. Beneficence, respect for persons, and justice are very important. What are these? Beneficence requires potential benefits of human research far outweigh the risk of the subject. Means the thing is, even if there is some risk, in getting the signal, biomedical signal, maybe in the invasive or non-invasive manner, especially in the invasive manner. But if its benefit for the humankind is huge, you can think of working and the ethically it is correct. Because see, you have people who are having severe paralysis. So those people can come forward, can volunteer to provide even their, what is called as a data where you require invasive data, invasive, data acquisition. That would give us more clarity, more analysis, better analysis, because we have understood that when you go deeper inside the brain, so you cover, very specific set of neurons. So your understanding, your analysis is always more impactful. And therefore, this is a very important factor talking about ethical issues. Second is respect for person. So when you are, asking the people to help you in the research, you need to have their consent, and that too, you have to tell them that what you are doing with their EEG signal, what you are doing, what you are going to do with their biomedical signal, and you have to get their consent in writing. That is very important. That is only ethically correct. Verbally, it is not correct. Sometime later, the person can say that I was not aware that you would be using my modalities in such applications. And what about justice? It requires benefits and burdens of research to be fairly distributed. I mean, there has to be benefit, but not burdening the, subject, not burdening in terms of research or in terms of risk and all that. Each of these principle is a very complex. These three things are not very simple things. They're very complex both in theory as well as practice. So there are challenges and risk. BCI research is a multidisciplinary involving neuroscience, physics, mechanical, electrical engineering. A lot of multidisciplinary areas are there. If you remember in the beginning, I was talking about cognitive science. So it itself involves a number of disciplines. So similarly, brain-computer interface research involves clinical neurology, neurosurgery, neuropsychology, rehabilitation, assistive technology, behavioral psychology, human factors. So, you need expertise, you need people, you need different domains to involve. And that is actually a real-time challenge, and it's a very challenging thing to especially involve all such people to get to reach to the very consolidated and good conclusion. So contributions from all the collaboration among the different disciplines are needed, and that is actually a challenging task. If you want huge success in the BCI research and its application, you need brilliant collaboration between or among all these multidisciplinary people and the domain experts. And of course, physical as well as psychological risk are always involved in this kind of study. What is physical research? You understand when you are capturing the signal in the non-invasive, it is minimum. But in case of invasive, problems such as skin irritation due to daily electrode application can be prevented in case of non-invasive. Even in non-invasive, you are placing the electrodes and putting some wet gel. So it may cause some skin irritation, but that's not a big problem. But physical risk increases when you go for invasive BCI. So you understand the risk which is involved, which is called as physical risk. Users need to be instructed how to recognize local or systematic signs of infection or implant malfunction. So when they have some infection due to your invasive modality, they must be able to understand with the help of symptoms that what kind of post effects they are having, and the treatment could be provided so that the risk could be avoided and could be addressed immediately. Psychological risk, if you take a person for your study, might go even deeper psychological problem, psychological difficulty might face. So BCI studies with severe disabilities run the risk of subject disappointment. You can tell them, you can tell him that we can do something with your modality. You can even think of rehabilitating them. And if it doesn't work properly, the person even can go, in more psychological problem and mental stress. So if it is not useful. So this may be mitigated, but not eliminated. This can be definitely addressed to some extent, but this psychological risk can never be eliminated. So we can emphasize the limitations and uncertainties, and we can just mitigate the problem by motivating and involving the subject's participation. And in order to minimize the psychological risk, a lot of research is going on, which is focusing on subjects who are ready to volunteer for the service for the mankind, for the society as the large, benefit. So informed consent, I was telling you, we need to take informed consent. We have to take the consent in writing, then only you can do some research. Otherwise, it's not a legal one. Process can be executed as long as the subject can understand by using some means of communication. So we have come to the last slide of this lecture, and after this we'll have one more small lecture. So looking to the future in terms of EEG signal analysis and its use in the cognitive ability assessment, cognitive workload assessment, developmental path from current state of microelectrode technology in realizing the clinical grade intracortical BCI interface to control prosthetic arm, hand with normal movement. I mean, let us think of developing prosthetic arm. Let us think of developing prosthetic hand that can help the people, in leading the normal life, in leading the normalcy in their life. And that actually is, the future research work where the researchers or the neuro centers are looking as a future of BCI. Highly focused engineering and scientific studies involving critical biological processes and device technologies are involved. Investigation of mechanisms of electrode performance, whether electrode can fail, whether electrodes are reliable, must extend beyond correlational analysis of tissue responses and electrode array performances. So there is a lot of scope of doing research in the quality, in the materials, in the fabrication of electrodes. Usefulness for BCI application always remains to be determined. That when you are having BCI, what is the use of BCI? Actually, whether it is going to benefit whether it is going to benefit the society, in the large scale, that is always a $1 million question. So the current science and technology base is sufficiently mature and robust to support progressive advances. It means a lot of science and technology, there has been advancement. I think that gives us confidence that there can be advancement in implantable microelectrode arrays, and that can really meet the required or necessary requirement in the clinical application. So there are challenges related to electrodes, microarray, microelectrode arrays, and the scientific and technology advancement could definitely address these challenges and could bring the better arrays for the clinical applications. Success also depends on careful utilization or selection of methods that incorporates knowledge of relevant and most critical biological, physical, and chemical factors, and they're all interrelationship. So this is all about discussing on workload, discussing on cognitive ability, and how the EEG signal as a brain signal and its processing helps. And interesting thing is how optimization method, AI ML method enhance or augment the performance of classification of cognitive abilities and cognitive assessment.